Hello everyone, I hope you're enjoying r2con 2020. Today I'm going to be covering a plugin I wrote to integrate r2 and Anger. This talk is pre-recorded, so feel free to ask any questions you have in the chat during the stream, and I should be available to answer them. So as we all know, r2 is a Unix-like reverse engineering framework, and Anger is a binary analysis framework developed at UC Santa Barbara and Arizona State University. Anger has many features, including IR lifting, program instrumentation, symbolic execution, control flow analysis, value set analysis, etc. And my plugin is a start to integrating some of these features with r2, though most of my focus was on the symbolic execution engine. Just as a quick refresher, symbolic execution is a way of determining what input values are required to reach certain program states. So normally when a program is executed, we'll provide it with concrete values that, amongst other things, determine which parts and in what order the program executes. With symbolic execution engines like Anger's, an interpreter follows the program, providing symbolic values for program input and computing the constraints for these symbolic parameters along each execution path. So in specifically the Anger implementation, the program is lifted to vex IR, and the program is interpreted by what they call the simulation manager, using what they call bit vectors as symbolic values, adding constraints to these symbolic values, which can eventually be passed to the Z3 constraint solver. Each path in the execution has an associated state, and at any point in the exploration, each state is in a stash or group of states, normally the active, dead-ended, found, or unconstrained stashes. So now I'm going to show an example on a simple keygen. So if we run this challenge, we can see it prompts us for a password, and then there's a success fail check, and in this case, we entered the incorrect password. So we can open this in r2. And if we seek to the main function, we can see the fgetS that gets our user input. Then there's a call to this function, which does a check. And then we have our success and failure branches based on the return value of that function. Now, normally we would just reverse this function, which is pretty small, so it shouldn't be too difficult. And the additional integration of the Ghidra decompiler makes it even easier, but we're lazy, and so we're going to use symbolic execution to solve this automatically. So all modality commands are prefaced with the capital letter M. So we're going to start by initializing modality and exploring to the main function. So we can see that this exploration succeeded, and the state is highlighted in blue. In addition to the highlight, all current active states are commented with their number, and we can see that this is state number 2. Now, this is somewhat unexpected, as we wouldn't think that there'd be any state splitting between the entry and main functions, especially on a Linux binary. And so to investigate this, we're going to list the states, and then we're going to seek to state 0. Now, from this ptrace call, we can infer that the purpose of this function is to check for a debugger, redirecting execution to this infinite loop if one is detected. And the Anger state splits whenever ptrace is called, which is why we have several states active. So we're not interested in the states where a debugger was detected, so we're going to kill them and then return to the main function. And we can see that our active state index is now 0. So to finish solving this challenge, we're going to explore to the success branch. And then we're going to kill all states except for the one that we're interested in using the MSE command for extract. And we'll extract state number 4. And then we can see that the state we're interested in is now index 0, and then we have all these dead-ended states. So now all we need to do is dump standard in for our state to get what the password should be. And we can see this right here should be our password. So we'll copy that, paste it, and that appears to be the correct password. Now, I went through this challenge rather slowly, but in an actual CTF, for example, we could solve it in a few seconds. Just to show you, I'll open it in R2 again. I'll use a different exploration technique this time. I'll explore until the string nice is in standard out. And then I'll extract state 4 and then get our input. And we've solved it rather quickly. Now we're going to solve a different challenge to demonstrate yet another exploration technique. So we can, once again, run this binary. We can see it expects user input. And then there's a success failed check, and in this case, we entered the incorrect password. So once again, we're going to open this in R2 and run some analysis. Now I can tell you ahead of time that the graph view in this main function is too large and complex to render in a reasonable amount of time. So I'm just going to stick to the linear disassembly. So I'm actually going to disassemble the first 1000 instructions and print that. And we can see in here there are a whole lot of calls to these two functions, maybe good and avoid me. So for anyone who has used Anger before, a common technique is to pass to the explore function a list of addresses for Anger to find or avoid during exploration. So similarly in modality, we can mark places with find and avoid comments. So if we list our functions, we'll try first seeking to the avoid me function. And we're just going to add a comment there that says avoid. And then we can seek to the maybe good function. And if we look at the graph view, we can see that the success branch after our compare is over here. So we're going to add a comment there that says find. So now all we need to do is run the explore command, me, and modality will compile these find and avoid comments and call the explore function for us. So it looks like we found a solution relatively quickly, despite the complex control flow of the main function. So we can see that here, this is active state 1. I'm just going to extract that to kill whatever extraneous state there is. And then all we need to do is get user input, and we have our password. So we can just quickly test that. And it looks like we had the correct password. So one general difficulty with writing Anger scripts is that it can be difficult to tell what the backend is doing during exploration. So modality provides a number of useful hooks to help visualize the backend. So to demonstrate this, we'll start by opening the r200 binary. All our hook commands are prefaced with mh. And so for the moment, we're just going to hook all functions. Next, we'll explore to the main function. And we can see here in our output our additional entry function calls. And this called a pretrace, which is once again used for anti-debugging. So since this binary has the same anti-debugging trick as the previous one, we'll extract state number 2. So next I'm going to demonstrate the loop hook. And so we'll run the command, and we see that our analysis detected 7 loops. And then we'll explore to this basic block on the right. So we can see in our output that some debugging information is printed each iteration. And this compare instruction is helpfully printed so that we can see this counter increment each time. And then also the malloc call is printed. So tracing is generally useful, but the main purpose of the loop hook is to ease with identifying path explosion points. So to illustrate this, we're going to explore to the end of the loop in this function. And we'll see our number of states rapidly grow. So we're getting a lot of output, and we can see that the number of active states is rapidly growing. 89, 144, 232. So obviously we're encountering path explosion. To solve this, we need to add merge points, but in the interest of time, I'm not going to demonstrate that today. So path explosion is a difficult problem generally, and I don't have solutions for that issue today, but these hooks should hopefully be helpful for people in identifying problematic code blocks. So I also have a few notes on state initialization. So in the previous examples, I just allowed modality to automatically initialize some state at the entry point before exploration. But this is something that the user has more fine-grained control over. So if I just open this challenge, show the help related to initialization. So with MIE command, I can initialize at the entry point, just like modality normally would automatically. I also have the option to initialize a blank state, which is basically just a empty anger state at some location. So there's a blank state. But more interestingly, I can initialize a state from the current debugger state. So if I start the debugger, continue until the entry point, and then if let's go forward a few steps, and then initialize from our debugger state. See, now we have a anger state where it attempts to copy as much information from debugger memory as possible and then initialize a state at that location. So now we're going to move to the next section, which will cover vulnerability discovery and exploit generation. Now, there's been plenty of previous work in using symbolic execution in automatic exploitation tools. See the DARPA Cyber Grand Challenge for examples. But there's normally been a wide gap between the manual exploitation process and fully autonomous tools. So modality is an example of a hybrid approach where much of the tedious and repetitive work is handled by symbolic execution and other scripts, while, for example, the higher level approach to vulnerability discovery is handled by the reverse engineer. This interactive approach is the best of both worlds, I think, given the current state of the relevant technology. Okay, so first I'll give a high-level overview of my current exploit generation implementation, and then I'll show how to use it on several toy binaries. To be clear, my implementation at this point is somewhat rudimentary, so for many reasons, you're not going to be able to run this on Google Chrome and expect anything useful back. But it's a start toward more sophisticated tools. So the first step of vulnerability discovery is a relatively standard exploration of all paths from the current simulation manager states. During exploration, it looks for states with unconstrained program counters. And when one is discovered, it attempts to constrain that program counter to an arbitrary value. If this is successful, we'll assume this is an exploitable state. So it then iterates through our symbolic buffers like standard in, checking which bytes are unconstrained and which ones need determinate values. And the result buffers form our base shellcode. The final step is to generate a payload based on our base shellcode. And this will include generating any ROP chains, bypassing additional protections, etc. And the result of this is written to a file and output on the terminal. So first I'm going to demonstrate how this works on the following basic exploitation challenge. As you can see from the source, it reads user data from standard in into a 20-character buffer using scanf, which can obviously lead to a buffer overflow. So next we'll open this binary with R2 and we'll load modality and list the help. As you can see, the exploitation functionality is under the ME command, both letters capitalized. So we'll run that to see what it comes up with. So after a few seconds, we can see it finds an unconstrained state, and then it constrains the program counter and loops through the standard in bytes, checking which ones are constrainable. So we'll ignore most of the terminal output for now, just looking at the base shell-coded outputs. We can see that the part of the shellcode that overwrites RIP is colored red. So now this example is somewhat interesting, but it's not really something you need symbolic execution for. This base shellcode could be generated much faster just by fuzzing and pattern matching. So next I'm going to show a variation on this toy binary where symbolic execution has an advantage. As many of you have no doubt experienced when writing exploits, oftentimes when attempting to get control of RIP, your buffer overwrites some earlier piece of data on the stack that is essential to program execution reaching the return instruction. So in these situations, you often have to spend 30 minutes in your debugger, altering your shellcode to maintain the original stack values to prevent the program from crashing. So symbolic execution, as we will see, can automate or at least simplify this process. So we'll take a look at this challenge, which is just the previous one, but with a slight alteration. If we look at the vuln function, you can see there's a couple comparisons with values on the stack, and the program will exit if any of these values are not what they're expected to be. So we'll just run the ME command once again. It's constraining the standard in bytes. And you can see here there's this skipped number, which is larger than before because there's a certain number of bytes that could not be constrained to an arbitrary value. So if we look here at our base shellcode, it's a little bit different. You can see that there's this byte here, and then these set of bytes, and these are the local variables for which there was a check that would exit the program if their values had been altered. So this is a simple example, but symbolic execution can solve for pretty complex shellcodes using this technique. So as we all know, binary exploitation has been significantly complicated by the introduction of protections like ASLR, DEP, etc. So Modality attempts to use, amongst other things, R2's built-in ROP search to generate shellcodes that bypass some of these protections. So I'm going to spend the next segment of this presentation just going over a few of the protection bypasses that I've implemented. So the first one of these isn't really a bypass, but rather a trick for CTFs. So often exploitation challenges have functions built in for the exploit to jump to. So Modality will attempt to detect any win functions and will dump shellcode that jumps to it. So I'll just show an example on this binary. We can see two function calls from the main function. One has our buffer overflow. And then there's this one, which has a call to system. So this is our win function. So we'll just show the exploit generation once again. constraining standard in bytes. And then we can see here is our payload for the win function. It guesses based on the call to system that this could be a win function, so it dumps the shellcode, and then it also writes this to win.txt. So we'll just test that. So a common mistake with these shellcodes is to run your exploit like so. If you're running your exploit like this, standard in and standard out won't be redirected correctly, and so you get the segmentation fault. So just one trick is to use cat. And it looks like we have our shell. Okay, so our first real bypass is going to be a ret to libc. So I'll first give a quick explanation of how this works for anyone that doesn't already know, and then we'll see how modality generates these payloads. So for the moment, let's assume that we can overwrite a return address, but the stack is not executable, so we need a ROP chain. One common way to get a shell via a ROP chain is to return to a function like system in libc with the appropriate argument on the stack. So let's quickly just take a look at how to do this manually. On this 32-bit binary, I'll limit our search space. And then first, let's get the address of system. See, there it is. And then we can search for the bin sh string. And there it is at that offset. So if your system is 32-bit, as per the calling convention, you'll want both addresses on the stack so that when you return to system, it will pull the address of bin sh as the first argument. Now, if your system is 64-bit, remember that the argument needs to be passed in RDI instead. So I'll just show an example of that. And there's our address of system. Then we'll attempt to find our bin sh string. And there's at least one instance. Oh, and then also we'll want to find and there's our prop RDI. So we can use the addresses we found to pop the argument we want into the RDI register, and then we can return to the system call in libc, and it will use that string as its argument, hopefully giving us a shell. So just to show how modality will do this automatically, we'll run our exploit command. Constraining standard in. And then here, it attempts to generate our payloads. Okay, so we can see it wrote our payload to this ret to libc txt. So we'll test that. And we can see we have our shell. So next I'll explain and demonstrate the ret to plt payload. So r2PLT is a technique similar to r2libc, except we return to addresses in the procedure linkage table rather than libc. So once again, I'll demonstrate how this works on our test binary. So if we list our sections, we can see we have a few here. And one of these is the procedure linkage table. So we'll see to that. We can see here these stubs for our imported functions. And the one that modality attempts to use automatically is this call to system. And so if we jump here with the appropriate argument either on the stack or in the RDI register, depending on your calling convention, you essentially accomplish the same thing as r2libc, except entirely within the binary. So I'll attempt to demonstrate this, running our exploit command. And here we have our payload. So I'll just test this quickly. Should be in the r2plt txt file. Actually. And we once again have our shell. All right, so to recap what we've done so far, we have solved some reversing challenges with symbolic execution. We've shown various state initialization techniques, including from the R2 debugger. We have used Anger to explore for states where the program counter is unconstrained for the purposes of vulnerability discovery. We've used this to generate basic exploits. And we've shown a few ASLR and DEP bypasses, which are automated as part of our exploit generation process. So looking forward, I plan to use some of Anger's built-in analyses to augment the analyses built into Raider 2. I plan to integrate the Symbian exploration technique from Anger. So Symbian is a somewhat experimental way to switch between concrete and symbolic execution that's built into Anger. So my method is kind of the naive approach of just copying data from the debugger into the Anger state. Well, with this technique, Anger reads data from the debugger memory directly while doing emulation. Now, the latter technique should be much better in principle, but for a number of reasons, it wouldn't work immediately with the rest of my tool, though I do plan to make this switch eventually. So I could also start tracking heap usage. Now, unfortunately, Anger's heap does not function like any sane memory allocator, which may limit the kinds of analyses that can be reliably built on it. But in principle, it could be used to detect use after freeze, double freeze, etc. So there's also more ASLR DEP bypasses to explore. I only scratched the surface in my talk, and Anger can definitely be used to generate like longer and more sophisticated ROP chains. There's bug fixes / increasing the robustness of the tool, and also Windows integration, which should be possible but is so far untested. And that's all I have for you today.